Until now, you mostly heard about fantastic storage devices, but I want to shed some light on an additional aspect of NAND devices, and its reliability. Something you usually take for granted, but as I'll show, it's not as trivial as you may think. You may want your device to actually remember what you store in it, but actually recovering the data requires quite a few operations. So what's on the agenda? I'll start with an introduction to NAND technology. So most SSDs today use NAND devices, NAND flash memories. So I'll start with an introduction of NAND devices and 3D NAND technology. Then I'll talk about their reliabilities and summarize. So NAND devices, NAND flash technology stores information as charge in a transistor cell. Transistor cells, basically, it's either a floating gate or a charge trap cell, depending on whether it's 2D or 3D technology. So transistor cells are chained together into strings, the columns that you see here in the image. And the way the sensing is working is that you store charge in the cell, and in order to understand if you actually have charge or not, you apply a certain voltage to the transistor. Now, you also apply high voltage to other transistors on the chain, and if the entire chain conducts, you know that the charge in the transistor was low enough to allow the voltage, the threshold voltage that you applied, to allow the entire chain to conduct. If it wasn't high enough, if there was a lot of charge in the cell, the VT threshold wouldn't be able to open the transistor and the chain would not conduct. So deciding which VT threshold or what position to put the VT threshold is an important aspect. We connect together many chains to form a block. So you have many blocks in a NAND device, a block made of many such NAND chains or bit lines, as we call them. Each block may contain several 100,000 or more such bit lines. We also define a word line as the set of all transistors corresponding to the same transistor in the bit line across the block. In order to store more information in a NAND block, we store more than just 1 bit per cell. And the way to do it is to store more than one level of charge. For example, in a TLC NAND, 3-layer or 3-bit per cell NAND, we store one of 8 charge levels per each transistor. However, programming, actually inputting this charge in the cell, is an analog process. It's not as accurate as you may think. If you look at planar NAND, for example, the latest technology for planar NAND was about 50 nanometer, and each transistor could hold only a couple of hundreds of electrons. So if you think about it, each level will only take a few tens of electrons, meaning that accuracy is quite important, but it's not ideal. So if you look at a collection of transistors, for example, a word line, you actually see a distribution of charge levels, as you see here in the graph, in the image here. So you get a distribution. Now, in order to distinguish between the levels, you must decide where to put your threshold voltages in order to distinguish what bit was programmed, what was the value of the bits that were programmed into the cell. Now, positioning these thresholds is a very delicate and important aspect of what the NAND controller does. If you get an overlap between those distributions, you will read it in errors, and you can compound the amount of errors if you also not position your thresholds optimally. So accuracy is important, and also it determines the programming time. The more you allow programming time to be longer, the more accurate you can be in your programming, but it's still limited. So as I mentioned, you can get errors, when you have an overlap between the distribution, and the VT thresholds positioning is critical. And the number of trials you try to read a NAND cell also determines the performance. If you try to add additional reads, it will cost you in performance and time. So there's a trade-off between reliability, programming speed, and read speeds. This problem becomes much harder, as you heard earlier from Samsung, when we look at QLC. Now at QLC, instead of having just 8 levels, you have 16 levels. So the distributions now are much, much tighter. Now a small error in your VT positioning will cause much higher amount of errors. And those positioning change over time, over stresses, which I'll discuss later on. So that's the reason why QLC is mostly intended for very dense and lower cost application, and mostly read-intensive applications. Programming or endurance reduces the reliability of the NAND, as I'll discuss later on. So now we are at a time where we're basically shifting from planar NAND into 3D NAND. In planar NAND, basically we put the bit line horizontally in one plane. In 3D NAND, we actually moved to building buildings, making buildings. And the bit lines now lie on a column. So the bit lines are columns in this image. And you have a collection of columns forming a block. Now, why move to 3D NAND? Well, in 2D NAND, as I mentioned, the number of electrons you could store per cell has become really low. Now, making the technology even smaller would make it much more difficult and much less reliable. Therefore, the choice was to move to 3D NAND. 3D NAND allowed to relax some of the technology node by adding additional layers or floors in this building. So you are able now to increase the capacity of the system. You also get a higher endurance because now you can store more electrons or more charge per cell. So you have higher reliability. This is why in 3D NAND now we are talking about enabling QLC devices, not just TLC devices. You also get higher performance. One of the reasons for higher performance is that in 2D NAND, typically when you were programming the NAND device, in order to overcome an issue called cell-to-cell interference, you would programming each word line in several steps. For example, 3 steps to program a word line. Cell-to-cell interference is a much less of a problem for 3D NAND, and therefore the programming of a word line is done in what's called a one-shot operation. One-shot operation of programming a word line, and therefore get much higher performance, also lower power consumption. So that's why we are moving now from 2D to 3D NAND devices. Lastly, in the introduction section, I would like to talk a little bit about NAND organization. So NAND devices, as I mentioned, are made of bit lines which are accumulated to form blocks. A word line would be a collection of all cells corresponding to the same transistor in a bit line. And a page, well, if we look at TLC devices or QLC devices, you may have 3 bits per cell or 4 bits per cell. So a word line would be a collection of cells, each one having 3 bits or 4 bits. So a page is actually corresponds to 1 bit within that, 1 bit layer within that word line. So a page is 1 bit, a layer within a word line. And the reason I'm mentioning is because we have different atomic operation in a NAND device. Programming is done at the word line level, reading is done at the page level, and the most important is the erase is done at the block level. Because of this fact, what happens is in order to manage NAND device, we might have some kind of management system. We would typically have a garbage collection in order to manage the NAND device and make sure we utilize it. Because of this garbage collection, we get write amplification. Garbage collection, basically what it does is goes over blocks which are partially used or partially superseded and copies only relevant information to new location in order to free up new blocks in the system. This introduces write amplification. Write amplification is the relationship between the number of writes you have from the host to actual writes you have from the NAND, which actually is much higher than those on the host. In order to mitigate the amount of write amplification, we have over-provisioning in the system, over-provisioning of actual physical NAND memory that is not actually allocated for user space. And this allows the system to reduce the amount of write amplification. I have here a chart that you can see for a relationship between the write amplification, between the over-provisioning and write amplification. So what are the roles of the NAND controller? Well, these depend on the application. For example, an SSD controller, a block type SSD controller, you would have a flash translation layer, which includes a translation from actual logical addresses on the host side to actual physical location on the NAND side. You'd have memory management and garbage collection operation continually working. You'd have wear leveling, taking blocks which have higher wear, higher program erase cycles, and replacing the data in them with those with lower ones. You also would have bad block management and so forth. In other applications, for example, open channel, you would go without the FTL. Mainly what you would want to use on all applications would still have is a layer that is responsible for the NAND reliability. And this is what I mainly want to talk about. For all controllers, you want to represent to the system, to the FTL, to the host, an error-free storage. So what are the requirements from the NAND? Well, you require from the NAND controller, require high throughputs, low latency with high IOPS. When you look at embedded application, on top of that, you also require very low power and low gate count. The result is unique ECCs and unique design to make sure that you can still support very high performance, but with very low power and low gate count. And of course, the NAND controller must adapt to all stress type, all conditions that the NAND can lie in. So what are the tools that we have in the NAND controller? Well, we have powerful ECCs that support both hard and soft decoding. Hard decoding is decoding best just on ones and zeros coming out of the NAND. However, we can also collect information about reliability per bit. For example, we can have additional reads at VT locations close to the optimal ones to understand whether the charge is close to the threshold or not. If it's close, it's less reliable than one that is further away from the thresholds. Decoding based on such information is called soft decoding. And of course, the ECC must support low gate count and low power. Also must have RAID capabilities. In order to optimize the VT location, we also apply unique DSP solutions. Utilizing machine learning. One of the reasons we must have unique DSP solution is there's a price or there's a cost for each additional read we perform on the system to understand its state. Performance price. And we want to minimize this price. And this is the reason why we apply unique algorithms such as machine learning. And of course, specialized management FTLs and to enable performance and reliability. So a little bit about the different stress types that we see on NAND device. So NAND device deteriorate under different stresses. And the first most trivial one is program erase cycles or program disturb stress. The more program and erase cycles a NAND cell undergoes, the more damage it undergoes. Each cycle has additional damage. And as a result, you will be able to see noticeable additional errors as the NAND device's cycles progress. This damage is much more apparent when additional stress is applied, for example, retention and so forth, or redisturb. But still, even without additional stress, it is noticeable. For example, if we look at a chart looking at the P cycles and the bit error rate, when we read the NAND data, we see a growing curve of the bit error rate as a function of P cycles. A major source for reliability deterioration is retention. Retention is the time that we spend between the programming and until we read. If we programmed the device a year ago and we read it now, it has undergone retention. And this retention may cause significant changes in the distributions. These distribution changes are much higher for blocks that underwent high PE cycles than lower PE cycles. And what happens with the distributions includes the following. Well, you see more charge loss as the device undergoes PE cycles. So you see the distributions becoming fatter and also shift. So your optimal VT location now shifted quite a lot, and the number of errors that you see coming out of the NAND is quite high now, because there's a much higher intersections between the lobe, overlap between the lobes. If you look at a chart of the bit rate as a function of the PE cycles, for example, if you look prior to retention, you see the bit rate increasing quite moderately with the PE cycles. If we look at the chart of the PE cycles after retention, if we have not modified the VT thresholds, you see it drastically increase, meaning that you can actually not use it without some significant operation on controlling on the NAND. So the NAND controller must adapt the VT threshold in order to allow the bit rates to not drastically increase. They're still higher than those that without retention, but can still be handled. And the NAND controller must do this automatically and with minimal marginal overhead. So the NAND controller must understand that the devices underwent retention and must understand where optimally to position the VT thresholds. So the bit rate still increased. This is why we must support very good decoding capabilities in the NAND controller and also support soft decoding, as I mentioned before. Another type of stress, so we've discussed retention. Another type of stress is read disturb. Read disturb is what happens when you read the NAND a lot. Basically, it's similar to a programming operation on a NAND. Programming operation is performed by applying a high voltage on the transistors and applying a current through the bit line. Reading is similar, but with a much lower voltage. So each time you read the NAND device, a small amount of programming is performed on the NAND itself. As a result, you get distortions of the distribution, this time in the opposite direction to retention. So for example, the race lobe and the lobe after that become fatter and they also shift. So you must also be able in the NAND controller to detect those modifications and adjust your VT thresholds and decode the increased bit rate. Also in the case of read disturb. A third type of reliability challenge is cross temperature. For example, when you think about a server room, you may have your drive being written at low temperature, maybe 25 degrees centigrade. And then when the system starts working and it starts reading a lot from the NAND device, the temperature can rise to 70 degrees centigrade. There's been a difference between the write temperature and the read temperature. And these differences can cause modifications or change in the distributions in the NAND device. This is even more crucial for in the vehicle industry. There you have embedded applications which require the NAND storage to work at a range between minus 40 degrees centigrade to 105 degrees centigrade. This is a very large gap in temperature. So you can write at minus 40 degrees maybe in Alaska, and read it in Arizona when the engine is working maybe at 105 degrees, and you'll get a very big shift in the VT scans. And again, the controller must identify this and adjust and decode. There are other failure modes that we must also contend with. One of these is, for example, sudden die failure or a sudden block failure. NAND devices can accumulate bad blocks over time. You have maybe thousands of blocks, 2,000, 4,000 blocks on a NAND device. And some of those are bad when they come out of the factory, and some accumulate more and more bad blocks over time. And you usually detect those bad blocks because you get a bad erase operation response or a bad programming operation. Or you can decide the block is not worth working with because you see that the bit rate starts increasing. However, there are some cases also where you suddenly discover you have a bad block when you're trying to read the block, sort of a catastrophic failure that you have not expected or not detected. For this reason, some of the systems also have RAID, or some type of RAID, where you basically store additional, per several blocks, you'll have a RAID block where you'll store some RAID function of the other blocks in that RAID block, such as to allow you that when you have a catastrophic failure on one of the blocks to recover the data and be able to copy the recovered data, the recovered failed blocks and all others to new locations. So these are many of the challenges that you have, and there are many more challenges that you have in the NAND controller. So to summarize, NAND controllers do much more than just FTL, flash translation layer. So you saw fantastic performance previously, but there's much more going on than just the FTL. You also have much more operation to make sure that the reliability is high. This is both similar and dissimilar to communication system due to the special requirements that you have from NAND device, for example, power, gate count, and also the additional cost for having additional NAND read penalty. NAND controllers use many methods to improve reliability. They manage the trim parameters of the NAND device in order to optimize its operation. For example, the VT threshold is one of the trim parameters. They use a unique ECC to support high performance, low gate count, low latency, and rate capabilities. And they also use a machine learning approach for lower overheads, improve accuracy and performance. The next generation challenges include QLC devices, which are enabled by 3D NAND devices. The reason is that, again, you have much tighter distributions there. Small VT estimation errors now will cause a large bit rate coming out from the NAND. So you must be much more accurate and must adapt your VT threshold much faster. And there are new trade-offs between reliability and performance. So now you have a trade-off between program speed and reliability. So you can expect QLC to be slower to program per device than TLC devices. The read time, gate count, and memory are going to change versus TLC devices in order to improve reliability. Thank you very much.